Okay, the topic of the day is this thing that I'm going to call gravitational field energy. In grade 11 and other times in textbooks online, sometimes we call it gravitational potential energy. But I did this cool workshop with the University of Waterloo prof, and he suggested we start calling it gravitational field energy because it's where the mass is in this bigger gravitational field that creates the energy. So they're kind of synonyms. Gravitational potential energy, gravitational field energy. I'm going to try and seem smart like this prof was trying to get me to do and call it gravitational field energy. It's one of my favorite lessons. I wish we could be in class so I could kind of talk you through this one. But alas, the current model, we're not in school. Hopefully it clicks. I'm going to talk you through it. I'll probably chunk this one because it's a fairly long document for a rather small outcome. But just to set up all the thoughts, it took a lot of typing. This first little blurb, this little chart up front, well, not historically, in grade 11, so I guess in your history, when we dealt with gravity, we often just used F equals mg and E equals mgh. Those are special case equations for the gravitational force and the gravitational field, and they work because, as I'm trying to show in this diagram, all these arrows are exactly the same size, exactly the same spacing. So we would say that the gravitational field, when we're close to Earth, is uniform or constant. Since it's uniform or constant, we can use those simple equations. However, if we back off, if we could zoom out and look at it, the arrows are no longer uniform. They're pointing in different directions. Their spacing is a little bit different. They're kind of close together down at this end, but they're farther apart at that end. If I wanted to draw the gravitational field really far from Earth, it would always point towards it, but those lines would get smaller, arrows would get smaller and smaller to illustrate that the field gets weaker and weaker as you're farther from Earth. Basically, we replace the Fg equals mg equation. When we're farther from Earth, we have to use this more general case, the gmm over r squared version of the force equation, Newton's gravity, or sometimes called the universal force of gravity equation. Just like we had to switch our force from mg to this gmm over r, we're going to have to replace our mgh with something more universal. When we're farther from the Earth, we can't use mg and mgh. They're special case for close to Earth. So that's that first little blurb in that first little box. Basically, mg and mgh aren't going to work, so we got to go through all this like 11-page document to come up with a new equation that does work. Okay, this is going to seem kind of random, but this next little blurb, it will connect and make sense later, but for now, just sort of trust me that it will make sense. I'm going with the idea that everybody taking this course, you're in grade 12, you're about to, let's say, move off to university. Some of you aren't in grade 12, some of you aren't moving out, but let's sort of roll with this little story. So imagine you're away at university, you're having a blast, you're working your butt off because that's what you do in university, you're making new friends, all that good stuff. And Sunday night, your mom calls and says, hey, we miss you. Use the app on my phone and I put $50 into your bank account. So you, of course, say, thanks, Mom, you're the best. Have a nice chat with her. Then after you hang up the phone, you check the balance on your mobile app and you notice that the balance in your bank account is 150. From that, we can infer the balance you had in your bank account before she put the money in. Everybody do a little mental math. You know how much money the person had before the 50 bucks went in? Okay, same scenario. Maybe it's later in time, Sunday night, your standard call home to your mom. Always make sure you call your mom on a Sunday night if you're not living at home. Hi, we miss you. We put $50 into your bank account. You have your nice chat. You're done chatting. You get off the phone. You check your balance. This time, after the deposit, when you hang up the phone and check, your mobile app says you only have $50 in your bank account. What can you infer about how much money was in the bank before your mom made the deposit? Okay, new scenario, same idea, a month later, Sunday night call, hey, we miss you, yada, 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 spoiled, rotten kid, I put $50 in your bank account. This time when you go on, when you check your balance, the balance is zero. If adding $50 to your bank account brought you to a total of zero, what can we infer about how much money you had in the bank before the deposit? Okay, the punchline in this one, the bolded point, If we add something positive and that brings you to a 0, then before the addition, you must have had a negative. We're going to need that later. It is going to apply to gravitational energy. So just file that away. Adding something positive, if that brings you to a 0, that must have meant you were negative in the first place. I'm going to pause this video and then start up a new one.